Welcome to another ASA ECR, another talk in the series of the ASA ECR Symposium series. Today we're very lucky to have Takafumi Tsukui, a postdoc at ANU, and today he's going to be talking about some of his work, which is really cool to me, which is about the emergence of thick and thin disks across cosmic history. Whenever you're ready.
Thank you. Thank you for kind welcome and hosting me. I will try my best not to make you. Okay. So let me start with introduction. So I'm showing you the common galactic structure in disk galaxies, and as you see in H1 view, you can see condensed flattened disk structure, and on that we have some galaxies exhibit spiral arm and elongated bar structures, and we leave out 8 kiloparsec from the center. And I'm always fascinated by the fact that our body, the element consisting our body is all from the stellar evolution and nuclear fusions. And this seems supporting our life as the hosting the efficient star formation and efficient element condensation to the gas. And also disk itself is gravitationally unstable to form spiral and bar and stir and mix the chemical elements, and eventually made our life possible. And that's why I'm very interested in disk structure, and ultimately I want to answer the question, Milky Way is special or not to support our life? And if it's special, what makes the Milky Way special in terms of maybe star formation, galaxy assembly history, and also the galaxy properties. So to answer those ultimate questions, we need to put galaxy in the context of the cosmic history. So, so I'm showing you the cosmic history from the Big Bang to the present day. And so, before the recombination, we see as cosmic microwave background, baryon cannot grow as it's coupled with photons. And then, but dark matter can continue to grow, its fluctuation. And then after the recombination, gas gets free and then fall into the dark matter halo, start forming galaxies. And 100 million years later, the first star galaxies start forming. And those tiny galaxies merged into bigger galaxies and more very chaotic phase. There's high gas accretion to the galaxies. And so maybe galaxies looks chaotic. And then later time, galaxy takes time to get matured and ordered structure as seen in redshift 0. So in that sense, galaxy can be separated cosmic history can be separated into 3 phases. Maybe the formation of the first galaxies, which is actively JWST contribute to this knowledge, but gives more difficult questions, and build up mass phase through the mergers and gas accretion, and then getting matured and ordered with less gas accretion and mergers. And today's talk actually concerning, so I have two topics. So one is concerning when and how did the earliest this galaxy form and evolve, focusing on highly resolved ALMA data at redshift 4.5. And then as a second part, I want to discuss how this galaxy built up from maybe proto-gaseous disk to mature Milky Way disk. So that's my plan. So let me start the first topic. So why looking at early disk galaxies is exciting and interesting? Because looking at the onset of the disk in universe tell us how the gas flows into the dark matter halo and how early galaxy form, how it look like. And here, as I said, before recombination of the universe, baryon is more homogeneous than the dark matter halo. And then after the recombination, baryons start to fall into the dark matter halo and start forming galaxies. And to think about the inflow, so we astronomers usually start with simplest model. So if you consider a spherical flow, then the gas so the gravitational energy converted to kinetic energy, and then gas collide each other and get heated to the virialized temperature. And this high temperature gas is thought to take time to cool down to settle into the disk. And that is a classical picture, and it may take maybe this predict the later formation of the disk structure about redshift 1. But as more complex physics into account, so like more accurate baryonic physics and more complex geometry of the outflow, then cold accretion is found to save this problem. So for example, cold accretion, the locally gas can cool down, and then this cold gas flow can penetrate into the hot gas halo and smoothly connect into the disk and form the disk maybe early as redshift 5. But yeah, of course, simulation is simulation, and we need to confirm observationally if the disk is already there or not. And of course, the baryonic physics is difficult to model. So from this kind of observation, and when disks start to form, give you the clue and improve our model of understandings. And these systematic studies, so these galaxies are systematically studied by KMOS team, and my current supervisor, Emily Wisniewski, as part of KMOS 3D, and they did very well systematically survey from 0.5, redshift 0.5, all the way up to 2.5, and they found already disky structures out there. And also they characterize the velocity dispersion, and they are increasing as a function of redshift. So galaxy is more turbulent in gas at higher redshift. And this study by Genzo 2017 inspired me, my basing my PhD student. They use gas kinematics to trace the mass distribution of the galaxy at even redshift 2.5. And I wondered if we can go beyond somehow at earlier redshift. And I was, in my PhD, I was at NLJ and Alma Regional Center. It's Alma Regional Center. So I think about how we can use Alma to go beyond the optical study from the ground. And Alma telescope is not telescope, like it's an array of antenna, 66 antennas simultaneously observe the single galaxies. And so that means we have large collecting area and very high resolution. And also C plus line, this is thought to be main cooling line of galaxies. So all the kinetic energy is converted to so the gas energy dissipate in this C2 line. So it's quite bright. That this is far infrared line, but that fall into the very sensitive alpha band 7 at redshift from 4 to around 6. So that gives you a very sweet spot kinematical study for this kind of redshift, far beyond the proved by optical so far. And I go through all the archives to find the kinetic signature that shows rotating, and I found these galaxies. So this is redshift 4.5, and this is originally identified as quasar, and it's currently brightest unlensed submillimeter galaxy known. So this famous object, that's why people already observe for these galaxies, and the dust emission distribution and C2 distribution shows a spiral-like feature, and also the velocity field is really looks regular. And also this galaxy shows a very high star formation rate of about 2,000 solar mass per year. But despite that huge star formation rate, it has dust disk, it's puzzling, and also, yeah, well-developed spiral structure, maybe bar-like structure, reaching to spirals. So, and also this source is taken just by one hour on source time, which is great compared to 33-hour observation for one single source. And to characterize more the morphology of the source, so firstly we found spiral-like features. So we decomposed the intensity map into different logarithmic spiral models. It's just like the Fourier decomposition into different sinusoidal waves. And this shows the spectral mode for the M equal 2 mode, 2-arm spiral mode, and peaked at pitch angle of 26 degree, so shown here. And by doing this, we identified the galaxy has 2-arm spiral structure with this pitch angle. And also, although the point spread function is elongated in this direction, there may be some elongated structure like bar, and this is seeing the peak, maybe this peak. And
so, sorry, can you go back? I'm really curious about this. So I can't do Fourier expansions in my head, so I'm curious if there's also a fitting component that then gives you the pitch angle as well as the 2 spiral arms, and are you doing that simultaneously with the other arms, or is it all separate?
Oh, these are all separate, and yeah. So you are wondering, I think these are also orthogonally.
Yeah, so I'm wondering if, okay, so you're kind of doing each fit separately. And so, because I'm looking at the M equals 1 peak, and there's definitely, looks like that could maybe be a solution, or am I misunderstanding?
Oh, yeah. So driving this mode and driving this mode is independent. And I just measure the strength of each potential component, and M equal 1, that means lopsided structure, and we interpret this strong peak as the lopsidedness between the 2 spiral modes. And the northern peak is stronger than the north. Yeah, southern peak is stronger than the southern.
And how does the angle come out? Is that just a fit? Like, I'm curious how they.
Oh yeah, so actually, so this decomposition actually integrate all the light effectively. So we lost the information of the phase So to draw this line, I just set one single value to decide which the initial angle of the spiral.
Thanks.
So there are hints of the elongated structure like bar. So we applied the classical bar finding algorithm that fit multiple ellipse, concentric ellipse to the galaxy isotope. And we found the characteristic signature in ellipticity profile and position angle profile to the nearby galaxies, where the ellipticity goes up and get flattened like bar structure from the bulge region to capture the bar structure, and then go down as you capture the disk component. And at this peak, there are position angle change, where the bar angle is in the sky is usually different from the disk position angle. So this twist capture this difference of the position angle bar and the disk structure. And we found the bar length is 3.3 kiloparsec. And interestingly, C2 bar is a bit thinner than 500 bar. And also C2 bar locate at the leading side of the 500 bar. And that I will get back later. So, but this kind of difference is interesting in discussing the bar dynamics. Yeah. And also, we characterize the dynamical structure of this source using the rotation curve. And I extract here. I'm showing the rotation profile along the major axis. I showed with color, and I modeled this distribution, velocity distribution along the Rhinium side with the 3D model, assuming rotation. Gas rotation with the bulge potential and disk potential. And we set the disk potential as the extension of the gas disk. And we found we need bulge to explain the very fast rotation in the center and extended disk to account the extended rotation curve. And we also found the dynamical mass is almost comparable to the CO gas mass. And that means the system, the mass of the system is 70% of the mass is the gas within this characteristic scale, 2.2 disk scale length. So this galaxy is gas rich and baryon dominated.
Also a kinematic twist, like the minimum and maximum of red and blue in the outskirts. Yeah.
Yeah, I will tell you later. It's very interesting. Yeah.
We're so curious.
Okay, thank you. Yeah, and also with this modeling and with the mass we found, disk is really, really gravitationally unstable already in terms of tumor Q. So it shows lower value of the tumor Q. And it was odd to me that gas-rich galaxy show this bad structure because previous, classical picture of bar formation, people studied the pre-existing disk with n-body stellar component, and then to see the disk star trapped into the bar orbit to form a stable bar structure. And in this process, gas is supposed to delay. Gas is found to be delay this kind of process, making the stellar bar. And tiny subordinate gas motion is studied in this bar structure. But in high redshift galaxy, as we see in the galaxy, example galaxy, baryon and disk mass is dominated, and these are gas-rich and turbulent. And so there may be a different bar formation channel. And I talked with Josh on this result, and he did new simulation, which include more realistic star-forming gas, self-consistent star-forming gas with realistic turbulent structure. And also gas is accreting from the halon, supported by accretion, and has high gas fraction. And in this gas regime, he found that gas-rich disk form bar are actually faster, faster than the N-body disk galaxies. And how they form is the gas form shear flow in the center like this. And in this shear flow, most of the young star form and form gas bar, young star and gas bar structure. So this galaxy may be with high gas fraction, and also there's a position angle offset from the gas bar and fine infrared young stellar bar, and the gas bar is thinner than fine infrared bar. That is actually consistent with what we see, gas shear flow and offset and young stellar bar. So to summarize, so this kind of kinetic signature, and also with high gas fraction, maybe we are starting to see new formation channel where gas disk directly form bar structure by star formation, rather than classical picture. These stars are progressively alternated to form bar orbit. And getting back to the non-circular motion, so there are interesting twist-like signature, and we subtracted the large-scale rotation with the kinemetry, and we found the interesting velocity residual, which is coherent and exactly coincide with the spiral arm structure. But it's odd to interpret as inflow, in-plane inflow or outflow, because if we interpret as inflow, these are in-plane motion, that means, so from this side, there may be inflow, but this side, it should be outflow. So it's very unnatural in this symmetric disk and having asymmetric inflow and outflow in gas. And also projection corrected velocity is 60 kilometer per second. That's 1/3 of the rotation velocity, which is very high. And now if we interpret this motion, m equal to pattern, as particle motion relative to the disk plane, then velocity amplitude is moderate, 40 kilometers per second, and this naturally explains the asymmetric perturbation, like U-shaped as in vertical direction, and this gas disk is actually stable against this kind of mode, so it can't produce such a mode spontaneously. So we need some external source to cause this kind of perturbation, and that may be gas accretion or merger. So in this source, maybe there's merger, and that gives high gas fraction and high intense star formation.
What was the velocity amplitude of the M2 mode was 40 kilometers. What was the amplitude of the third and the fifth mode? Oh, was it also similar to the M2 mode?
Oh, I need to. I will show you later.
Yeah, sure.
Yeah, but it's smaller than M equal 2 mode. Okay, so but actually this kind of mode is seen in simulation as well for well-developed disk. Disk is very if disk is massive enough, it's very responsible to the external perturbation. And in Milky Way, Sagittarius dwarf interaction cause the spiral arm, spiral density arm, and also coincided position. There is also the vertical motion as what we see in these galaxies. So that means this galaxy, spiral arm, is caused by external perturbation, and it is likely a density wave induced by this external perturbation. It's the well-developed disk. So the first part summary is that the galaxy can already have this very high star forming phase, and these are extremely high gas fraction, probably supported by gas accretion from the merger, cold accretion that induce disk spiral wave, and also bending this vertical perturbation. And also the bar is consistent with the maybe young star directly produced by star formation in the gas shear flow. And that may also promote bulge growth. And so with this study, we extend this gas velocity up to redshift 4. But yeah, recently many more ALMA studies produced the plot from the C2. And interestingly, C2 observation gives a smaller gas velocity dispersion that may be different, that trace different ISM phase. And we don't really know the multi-phase structure. That is interesting to explore more. Yeah. And so the second, as a second topic, so we understand the disk can form very early, and how these disks then evolve into from gaseous disk to matured Milky Way disks. So getting back this plot, we know that Milky Way is not just single disk, but more complex. We have cold disk, called thinner disk, and thick disk. And thick disk has old population, stellar population, metal pore, and also high enhanced alpha abundances. And thin disk is thinner but young and metal rich and low alpha abundances. An alpha element is produced by Crab's supernova. So to enhance this alpha abundance in thick disk or any structure, you need quick star formation and then quench to produce contaminated by later chemical yield. So that may already tell us thick disk may be formed in short time. And so Milky Way is one of the baseline for this understanding from the Gaia and spectroscopic observations. And in creating two-disk structure, there are roughly two ideas. So gas may form fast in turbulent disk and thick, and then gas dissipate and get thinner and form a second disk to form double disk structures. And there may be later heating scenario. This can actually form in thin and then get scattered into higher altitude by local density perturbation, something like molecular clouds, clumps, spiral and mergers, and produce this kind of two-layer structures. And these are currently under debate, and we cannot tell which is more likely or not. Just studying redshift 0 galaxy, because many of the information lost. And so studying two disks across cosmic history is very essential. And relating to the previous topic, now, so there are velocity dispersion evolution as a function of redshift, and later earlier time they are more turbulent. So that may fit into this scenario, but our study recently showed the cold gas disk, which may form the thin disk early enough. So that complicates this formation scenario. And also, we start to see old thin disk in Milky Way, and that complicates the situation. And maybe two scenarios is not exclusive, but also mixed. But the problem is we don't know at all the two disk structure as a function of redshift. We only know redshift 0 galaxies, and roughly thin disk has 0.2 kiloparsec width and height, and thick disk has 0.4 kiloparsec height. And recently, using shorter JWST shorter band, Liang proved the thickness of the disk as a function of redshift and found declining trend. But the limitation here is they are only tracing the young stellar component with shorter band, and JWST provide less frame near infrared band that trace stellar component, the stellar distribution that may give us a comprehensive understanding of these two structures. So with this objective, we exploit all the current JWST public image to gather largest edge-on sample using many these selection cards and careful visual inspections. And also this edge-on configuration give us the height of each disk, and also best signal to noise because the line of sight goes through the disk. And so yeah, as I said, JWST provide less frame near infrared band, which is a great stellar mass tracer. And so we can trace short band up to 1.3 redshift and 2 H band and up to redshift 2 and J band up to redshift 3. We use this band at different redshift to minimize the dust extinction and secure the better mass sensitivity. And for the sample of edge-on galaxy, we fit a 3D disk model with the radially exponential and vertically sec square function. And with single model, for this galaxy, redshift 0.7, there are excess light above the disk midplane. And here, I'm showing you the vertical profile at each radius. And there are systematic excess at this radius at all the radii. Then, so we added second component. Then this systematic excess is accounted by using two components. And also there's a bulge component remains. So we added one bulge component. So by doing this, we measure the structural properties of thick and single disk for the first time at cosmological distance, for example, 0.7 redshift. But not all galaxies can be fitted by two components. Data may not allow some of the galaxies, faint galaxies. So we carefully choose the best model given the data quality using the Bayesian information criteria. And so if BIC is improved by 15, then I allow a more complex model from single disk to double disk, plus bulge and plus bulge. and then visually inspect all the galaxies if the model is fit to the intended structure in the actual bit. And sometimes bulge becomes a thin disk. So in that case, I reclassified into the two-disk galaxies. Because bulge profile is very flexible, so it can fit to the thin disk. But if we can tell, oh, this is obviously thin disk, then we declassify. And with this measurement, we found so we call single disk for galaxies fitted well with one single component, and thick disk and thin disk are two disks identified in the galaxies fitted by two components. And actually, all the disks follow the strong scaling relation for this scale length and scale height and the ratio between the two. So this kind of scaling relation is already set by explored epoch up to 10 gigayears for two disk and single disk for up to 12 gigayears. And our measured scale height consistent with Milky Way in vertical direction, but in the size mass relation, Milky Way, we confirm the long-standing observational suggestion of Milky Way disk is relatively shorter than other galaxies. But recent studies show broken exponential that may close the discrepancy. And most strikingly, very interestingly, single and thick disk occupy similar region. That means all the galaxy classified as single disk has single thick disk. So galaxies start to form thick disk first and then start forming thin disk. That's the implication from this association. And we studied the disk property evolution as a function of look-back time. And as expected, there's mild increase reached to the redshift 0 point for scale length, the radius, and vertical height is mildly increasing. And also, but the disk length and height is constant. So mechanism responsible for this growth preserve the geometric structure. And this increase is actually contrasting with the previous finding in shorter band. They are saying strong decline as a function of redshift. I will revisit the next slide for this. Oh, and I forgot to say, this red median points are mass corrected, because different redshift can be contributed by different mass. So I used the scaling relation to correct this kind of mass bias in this plot. Yeah, so for single disk, only looking at single disk, the mildly increasing is contrasting with the previous result, but thinking that their observed band is tracing much shorter band and tracing young stellar population. This is consistent with what we're seeing. Thick disk form fast as single disk, and then galaxies start forming thin disk later time. So at the early time of thick disk formation, this shorter band trace their ongoing thick disk formation. But the galaxy transiting into thin disk formation phase, and that outshine in short JWST band, and that actually start align with the thin disk scale height in this study. yeah, so to summarize, so we, for the first time, we explored two disk structures up to redshift 10 gigayears. And stellar mass and radial vertical disk size relation was set already 10 gigayears ago to 12 gigayears ago. And we established with this time resolved sample across cosmic time, spanning cosmic time, we established the dominant two disk formation, a thick disk first, and then thin disk form later. Okay, so yeah, many more to come with the paper shortly out, and with growing sample by JWST observation. Oh yeah, so yeah, this kind of picture is suggested for the explored epoch, but maybe more complex things is going on. So let's see. And yeah, this is last slide. So yeah, what we see in bad galaxies, early bad galaxies, and also yeah, JWST result. So so by looking at external galaxy, we can complement the understanding of thick disk and thin disk formation. And I wanted to show this plot from Shuka 2014. This is a very busy plot, but it's plotting the Milky Way disks, Milky Way stars as a function of stellar age and the metallicity. And galaxy, so all galaxies are forming thick disk and thin disk. Blue are point alpha, red point is alpha enriched, enriched stars, and blue are point less alpha abundant stars. So that means thin disk has prolonged star formation. And she see the dip, and probably due to the merger that make the stellar metallicity goes down by mixing. So metal for gas is flowing, and then gas-rich starburst may happen and shut down instantly, and then forming thin disk. And at the same time of the gas-rich merger, bar formation is suggested to form. So by studying, so maybe this gas phase bar formation can also work at Milky Way. So yeah, by studying Milky Way external galaxy, we can also provide information to the Milky Way study. Thank you.
Okay, do we have any questions? Man.
Yeah, that's a great talk. I was just wondering about the formation history that you propose, which is that the thick disk forms first and then followed by the thin disk formation. I was wondering whether your sample selection of just looking at the isolated objects could somehow systematically prefer one of the formation histories to the other, because if it's isolated, then I guess is it less likely to have mergers happening around it, or is it not so isolated?
Yeah, that's a good idea. So our sample is biased to the thin disk because we cut single axial ratio, and that may be, so bulge dominated galaxies probably excluded by this single cut. And that's because we don't want to include the large inclination that also bias our measurement. So for this first exploration, we use single axial ratio and stricter cut, very strict cut to remove the inclination, not perfect edge-on sample. But I think looking at the axial ratio distribution as a function of radius and somehow include the bulge contribution, account the bulge contribution and maybe we can expand the sample of these those kind of disk, not isolated, maybe bulge dominated, and then that's the future work to include those sample and different formation paths of the different disk galaxies.
Sarah?
I was going to ask a very similar question, so I'm going to follow up on that. So if you go to Joe's work on your final slide, if you look at that, you might naively assume from that that the thin disk in the Milky Way, or at least the thin disk in the Milky Way formed from that merger and that merger and that subsequent star formation. So therefore, the systems in your sample where you're then seeing, thick disk has formed earlier, but some of them do have a thin disk. And if the Milky Way, if that thin disk could have formed through that merging, if these galaxies are isolated, then it seems like they wouldn't have that same evidence for that merger-induced formation of the thin disk. Does that make sense?
Okay.
Maybe it's a too simplistic argument, but it's. So I was curious. I was going to ask if we study tidal features around nearby galaxies, and we're curious about how those indicate signs of merging. If you've picked kind of quite pure, quite isolated galaxies, then they've not had recent evidence of mergers, which would make then the thin disks there potentially different to what you're seeing in the Milky Way.
Yeah, that's a good point. And we want to encompass all the formation histories, and visual inspection was a huge task. And
You only had 111. He had 4,000.
6.
6. I forgot 2,000.
yeah,
It's fine.
so I think in the end, I want to include somehow disturbed galaxies and different formation paths, and that's, I think, machine learning, those kind of things help. I don't know. And how we can better quantify the width or this measure, because if there are this disturbed morphology, that also bias our measurement. So you want to see what's the limit of this.
That'll be really. It's already very interesting. Extra interesting.
Anyone else? The C+ line, do you know exactly what phase of gas that's tracing? Is it cold gas or warm ionized gas?
Yeah, I think it can be everywhere because
Right.
Low ionization potential and can be excited in any phase. But also it depends on the star formation rate of the source, and I think galaxy properties. I'm aware some of the paper explore which phase C2 allows, depending on the galaxy properties, energetic properties, such as radiation field.
Right, and actually I had another question about this galaxy. Is it really compact for its redshift? Like it's a very compact galaxy. Okay, so that's interesting that you can get a buckling warp in something that's super compact, because I imagine that'd be really hard unless you just really punch right through the galaxy. It's really cool.
What's the scale in kiloparsecs?
So it's, I think, 4 kiloparsec. So 8 kiloparsec.
That seems right. That doesn't seem that compact.
Yeah, okay, right. Well, it's at a redshift of 4, so I thought
Radius of the disk is 2 kiloparsec.
Okay, right.
You can see here this dip here and here. So it's about 3 kPa. Yeah.
Anyone else?
I think, yeah, for this mode, I suggest it's very interesting because this M=2 mode do not degenerate with the rotation because M=2 mode is orthogonal to the M=1 mode that's from the rotation and also radial motion that is also seen in M=1 mode. So this is robust detector of maybe the perturbation to the disk or merging and accretion. So I want to do more with different data. Yeah.
Just got an anecdote. So kinemetry, are you using Davor Krasnovik's code for the kinemetry?
I'm using Python code, I think.
Yeah, from Krasnovik, yeah. I met him maybe 2 years ago or something like that at a meeting. And then I told him I have a student working with kinemetry. And he was like, people are still using that. Like he thought there was nothing else to be done with kinemetry. So I was surprised to hear him say that because there's such a such a good tool. I was like, oh, well, fine. If you're not busy with it, we'll be busy with it. It's great. So yeah, more evidence that it's actually a very useful tool.
That means he stopped perusing the literature on it as well.
Yes, that's true, Greg. It's still very much in use.
Okay, cool. If there's no other questions, Takafumi's going to be around for the rest of the day and then some. So if anyone has any extra questions, he's in Nandini and Christina's old office, which I think is now the postdoc room. So feel free to find him if you want to talk to him. But yeah, that's a wrap for this one.